Hi, so this is class 7 of SC418, where this week we'll be talking about, I think we'll be introducing a few more statistics for you to analyze the course data sets and also your own project data sets. So we'll take a look at the worksheet. So note that I have actually changed the final questions here. It's final exercise just to make it a little bit more clear. And to sort of make a better point. So this may be different if you've already looked through these exercises. These may look different to the ones you've already seen. So here you're asked to look at the same 7 data sets as before, and you're introduced with three new functions. So note that so there's also a PDF file which describes this PCA, which is principal component analysis. But also we look at the space-time separation, which is something that we looked at in the lectures, and then you gave a lecture about 3 or 4 weeks ago, and this partial autocorrelation. So let's just briefly describe what each of these mean. So firstly, you're asked to plot the autocorrelation up to lag 20. So you may have come across the partial autocorrelation. It's a sort of standard statistical measure, and what it does is it looks at the linear correlation in a time series, but actually what it does is take into account the previous lags. So for example, if you're looking at the partial autocorrelation at lag 2, then what you're looking at is what you're trying to find is the correlation, the added correlation. So once you've taken into account the lag at lag 1, so if you say you have an AR1 process, you expect there to be autocorrelation with lag 1, but also lag 2. But the time series is defined in such a way that it depends only on lag 1, and the only correlation with lag 2 is because we have this sort of time series of things where, of course, if xi is correlated with xi plus 1, then xi will also be correlated with xi plus 2. If xi plus 1 and xi plus 2 are also correlated, so you take into account this thing. So the partial correlation is often used as a way of determining the number of lags to use in an AR process. So if you have an AR1 process, you'll find that the partial autocorrelation is around 0 at lag 2, whereas the autocorrelation itself will be greater than 0 because you've already taken into account what's happening at lag 1. The partial autocorrelation disappears. Okay, so in terms of uses, it's a really useful way of doing that, of looking at linear correlation and trying to determine the number of lags or the value of P in an ARP process. Next, we have the space-time separation plot. So Lenny introduced this, and the idea of a space-time separation plot is simply to plot the distance between 2 points in the time series as a function of the lag time. So if you think about a continuous process at small separations in time, then the correlation, the distance between, say, at time 0 and time tau is going to be quite small. Whereas the further the time series goes, the higher the sort of lag, the bigger the distance. The space-time separations plots tell us all sorts of things, and I'll explain what those mean by looking at the data sets. Thirdly, we have the principal components. So there's a worksheet on this, as I say, and the idea of principal component analysis, you may well be aware of having in it from other courses, is simply to try and reduce the number of variables. So often we have, so this is sort of a general case, but we have a bunch of variables that may be correlated in some way, and what we want to, and often these sort of share information. So, for example, if you look at the height of someone and the weight of someone, these things are going to be correlated, and there's a large overlap between what they tell you. So the principal component analysis effectively tries to find new variables that are a linear combination of the kind of existing variables that are orthogonal. So whilst height and weight are correlated, and the new variables will not be. They'll be orthogonal to each other. And the idea is then that if you have a lot of correlation in the time series, in the variables, then we can reduce the number of variables. We can get as much information from, say, 10 variables than we could from 100 variables. And the principal components tell us how much of sort of variability is explained by each variable. So these are done in order. So the first variable that you create from doing this has the biggest amount of variability, followed by the second, etc., etc. In terms of the time series, here we use principal component analysis on a sort of lags time series, and the idea, it just tells you really if the principal components decline quite quickly, so the size of the principal components go down quite quickly, then this means that that there's a lot of correlation in the time series. So if you've got, say, a continuous time series that's observed on a regular basis, like at regular time intervals, then we expect the principal components to go down quite quickly because, lag 1, lag 2, lag 3, etc., have quite a lot of shared information. Whereas if we had say, white noise, we'd expect the principal components to decline slowly because they're completely, each time step is completely uncorrelated. So what does this tell us about time series? Well, actually, it tells us very much the same kind of information as the autocorrelation. So let's look at some of the data sets that we have. So first we'll look at gluttony, because I think that's an interesting thing to look at for the case of the partial autocorrelation. So we scan this in, and we get time series, 2048 steps. We can find a partial autocorrelation up to however many lags we like, 20, say, and then we plot that. So here, actually, interestingly, the partial, at lag one, by lag 0, of course, the autocorrelation is 1, but at lag 1, it's around 0.4, and then it sort of declines. So actually, we see some inflation in the lags beyond the first lag. So this implies that we think this. So we looked at this with 1.4, and we think this is a linear process. In fact, it is a linear process, but this sort of suggests that it could be an AR process up to two or three lags. Perhaps it's not so easy to tell, but maybe 2, but it could be 3. Okay, so we can actually compare this to what we see in a past exam paper. So this is the 2017 paper, and this is a question 3, which this is called compare and contrast the time series. So this is 3C. So we can see this is a linear process. The histogram is Gaussian. The differences in the histogram of the differences is Gaussian. The delay plot looks very, very linear, and we can look at the partial autocorrelation, which is this one here. This is the sample partial autocorrelation function, and we see that actually at lag 1 we have this we have significant partial autocorrelation, and then this just goes down to around close to 0. So this really does look like an AR1 process. This gluttony data set looks like it could be an AR2 or an AR3. We can then look at the partial autocorrelation of other data sets. So it's less clear how to interpret these if they're nonlinear, for example. But let's look at pride. So this is a so this is a low-dimensional nonlinear time series. So again, we can plot the partial autocorrelation of that, see what happens. And there's a bit of a pattern here. We can do more. We can do a few more lags as well if you like. Say 50 if you like. And yeah, it really doesn't look linear. So this doesn't decline down to sort of bounce around 0. we had some partial autocorrelation. Actually, the chances are this is a Markovian process. So only the previous step actually um, only the previous step actually determines the next step. But because we're looking at linear correlation, not all of the dependency from one at lag one is sort of determined from the autocorrelation, your partial autocorrelation. So we also see some patterns here for longer lags. But really, partial autocorrelation is not a particularly useful measure for nonlinear processes. So finally, we can look at anger. So anger is our sort of real data set, which is returned from stock. We don't expect there to be any autocorrelation here, so we can see what happens if we plot this. Like that. So here we see, so there's autocorrelation lag 0, of course, and then it just goes around 0. So we see that this is it's not white noise, but it's there's no kind of autocorrelation going on here. So the next thing is the space-time separation plot. Now, space-time separation plots are actually very useful. So let's start with gluttony again to see what that looks like. This shouldn't come as a surprise. This is a linear process. So how does this work? Right, so we have STSB, space-time separation plot. X is the first. Is the first argument. The next one is the number of the maximum time ahead we look. Maximum lag. Let's try 100, and then we have the percentiles. So actually, with a space-time separation plot, we don't just look at the mean separation between in the whole time series. We look at quantiles or percentiles in this case. We look at sort of the distribution of this. So we can look at all of the numbers between 10 and 90, between 10, 20, 30, 40, 50, 60, 70, 80, 90, by creating a sequence like this. Takes a little bit of time to run. And here we get the space-time separation plot. It's not particularly surprising. We can look a bit closer at shorter lags, and we see that gradually over time, the time series just gets further apart. It's not surprising. There's also correlation in the time series, but eventually you lose memory. Okay, so really the key thing about space-time separation plots is the stage at which you lose memory. So once these contours go flat, at that stage you don't really expect to be able to forecast the time series because the information in the initial condition is effectively gone. So let's look at something a bit more interesting. So look again at pride. So this is the low-dimensional time series, low-dimensional nonlinear dynamical system. Again, we create a space-time separation plot. So here things look a lot more interesting. Here we see this sort of. So note that a property of linear series is that we never expect to get back to where we were. So for the longer the lag, the further away on average we expect the distance to be on the space-time separation plot. We expect it to go up and then flat. For nonlinear systems, we can have recurrence. So remember, you may recall that we talked about recurrence and periodicity. So periodicity is when a time series repeats itself. So for a periodic time series, you expect these contours to go back down to 0, then go up and then down and up and then down. For a current time series, you don't expect to ever go down to 0, but you do see this kind of returning back close to where you started. So here it's very clear that the time series sort of goes back to where it started. That it goes up and then it goes back down again. Here recurrence, it goes up and down, and this keeps on happening. So eventually you sort of lose information, and eventually these go sort of somewhat flat-ish, and then you'll find eventually you just go flat, fairly flat, and then you'll lose. In the end you lose memory in the plot. And just for sort of completeness, we can look at the anger data set. So anger, again, if we have no autocorrelation or no independent points in the time series, then all of these are going to be flat. All the contours are going to be flat, or roughly flat. And this is what we see. So then finally we have the PCA. So let's go back to gluttony, the linear time series, and see what PCA looks like. So we need to load in PCA function, and all this does is just gives you the principal components. So the larger these numbers are, the more important, the more variability described by the new variables. So here, 88 is quite high, and then so the first principal component describes quite a lot of variability, then it goes down and down and down, but not that quickly. So we can look at more principal components. So yeah, it sort of declines over time, but not that quickly. So because there's some autocorrelation in the time series, we expect these principal components to go down sort of fairly slowly. So we don't have if it's white noise, then the PCA would all of the new variables would have similar amounts of importance. But this goes down fairly quickly, suggesting that just looking at shorter lags can tell you something about longer lags. So we can describe the lags in the time series using a smaller number of variables because there's correlation in them. So we can compare this to the anger data set. We can do the PCA again. Yeah, and again, I guess this goes down fairly quickly. We can take a smaller. No, sorry, it doesn't go down very quickly at all. So, and that's because you can't describe these uncorrelated data points using a smaller number of principal components. So the question really is: so how important is principal component analysis? I would say it's one of the less important statistics you're given in this and in the exam. So it tells you it sort of effectively tells you something quite similar to autocorrelation and things like that. So let's look at these final three things. So here you asked to create a time series of data that's a sum of trigonometric things, so sine and cos, and make a space-time separation plot. So this has changed since earlier, so I updated this slightly. So what does this look like? Well, we can define t between 1 and 10,000 very easily, and x is just 2 times sine. So this should be, so we need t times pi over 16, and cos of t times pi over 16. And we can plot x, see what it looks like. It's not what it looks like. So we've got only the first 100 points or something. Yeah, so we see that we have this recurring thing, this periodic thing. So we can make a space-time separation plot. by doing this. We'll see what happens. So you see that here, okay, so here we haven't really looked at enough time lags. So let's do it up to 100. So here you see this is a unsurprisingly, this is a periodic time series, and the space-time separation plot tells you this. So you get further, so the time series gets further, for certain lags, the time series gets further away from each, the points in the time series go further away, but then they come back together again. And eventually they go back down to 0, and it goes up and down to 0. So of course, once you go down to 0, this means that if you've got a deterministic system, which this one is, you must have periodicity. By definition of periodicity, if for some tau, the points in the time series are the same, then of course you must repeat. It must repeat forever and ever, and that's not surprising for this time series. So then you asked to compare this to the Pride dataset. So we call that Y, and we'll just make the space-time separation plot. Okay, so we do this. Let's do this at a shorter window. Okay, so we really looked at this, but again, you can see the difference, right? So in the sine and the cos, the previous time series, we've got periodicity. It goes back down to 0. Here we have recurrence. So this is a key thing here is the difference between periodicity and recurrence. A periodic time series repeats itself exactly. A recurrent time series gets back arbitrarily close to where you started, but never hits that point. So you end up with this sort of repeating behavior. And the space-time separation plot allows you to show that. Note in terms of forecasting, predictability, if we've got this sort of pattern like this, we can see this variability. This implies that there may well be predictability at these sort of time series, these kind of lags. For longer lags, once it levels off, then at that point we don't really expect for there to be any predictability. Okay, so I think that's all for this class, and we'll finish up there. Thank you.